As more organizations attempt to define the structure of their internal model-based systems engineering, or MBSE development processes, some are also considering the virtues of performing an interdependent model-based safety analysis, or MBSA, as an integral piece of that process. This video will describe an overarching process that enables the MBSA to be performed as an interdisciplinary design activity. Model-based diagnostics engineering must be performed at the same elite level as the MBSA to ensure the precision and utility of the data as it transitions from development to the operational and sustainment lifecycle. As MBSA expands in popularity, diagnostics engineering shall provide the currency to trade, balance, validate, and ensure that the benefits of the MBSA are able to make the seamless transition across design disciplinary boundaries and then realize in the operational environment. At the core of the model-based diagnostics engineering is eXpress, which is not only interoperable within DSI's ISDD model-based tools, but also with data from any capable third-party reliability or MBSE tools. The eXpressML data import to Express is used to capture functional data structures from industry MBSE tools, but also avails an XML output for reuse in other high-end aspects of the MBSE environment as well. Express enables all of the functional and failure propagation to be captured in its hybrid knowledge base that's interoperable with the myriad of data sources. Data forms such as SysML or MSXL can be imported into Express, where the data can be immediately cross-checked and validated for consistency, completeness, and accuracy before it is moved further into the process. MBSE tools do not typically contain comprehensive failure data or diagnostic information, as is essential when attempting to optimize and influence design decision-making. Contrarily, by leveraging Express, significantly more integral data is immediately integrated within a dynamic product lifecycle management, or PLM paradigm. In ensuring the integrity of the MBSA, the diagnostic interdependencies shall provide the means to cross-validate any interdisciplinary design assessment products. With this knowledge base, the test coverage for any bit can be validated. In Express, one way to validate your diagnostics is to run the fault insertion report, which can show how the diagnostics isolates random combinations of failures. Let's do 20 combinations of up to 2 failures at a time. We'll include the fault signature and test sequence for each failure combination and generate the report to a spreadsheet. For each failure combination, the report lists the test that would fail and the test used by the diagnostics. The auto-generation of testability assessments is a core competency of Express by delivering a rich and unmatched set of documentation in support of any complex design. Express is able to auto-generate preliminary failure modes and failure effects for any design. When more specific data is available, it is imported or merged into the model and fully propagated throughout the design. Since Express inherently propagates root failure modes, failure effects, and relevant component property attributes throughout the entire design hierarchy, the preliminary functional hazard analysis can be auto-generated as an output product and/or described in a form that is traceable and mapped to the WBS. Express is able to automatically generate the traditional, standard FMEA or FMECAs while allowing full customization. Additionally, Express enables the FMECA to describe such diagnostic details about each component as failure detected, number of root failure modes in each fault group, and the size and constituency of that fault group. It can also describe if the failure is uniquely isolated, being identified as FUI, which is key to considering any root failure causes. Not fully discovering the impact of FUI will have a negative impact on the operational value realized from any MBSA. The Express Fault Tree Analysis, FTA, is produced as an output from the captured diagnostic design in Express. Unique to the Express FTA, it will identify the probabilities of detecting a failure at any node of the FTA and the percentage of that failure that can be uniquely isolated, or FUI. This is key to identifying the root cause to a specific failure mode at any node in the FTA, integral to a high-end MBSA process. The inability to discern the specific root cause is a heavy contributor to false alarms and operational aborts. The simultaneous auto-generation of Express Diagnostics informed FMECA and the interdependent Express FTA can be performed at any point during design development. Concurrently, automated cut set reports for any FMECA FTA generated in Express can also be reflective in a failure mitigation report to discover mitigated single-point failures. As these companion assessment products are generated as codependent outputs from any model within Express, any variation, change, or update to the Express model during the development process can be immediately integrated with the corresponding MBSA and included in ensuing trade study analyses. To discover the strengths and weaknesses of the MBSA as it corresponds to the operational environment, the data can be exported to an operational support simulation whereby any failures can be simulated during any mode or operational state of operational asset. The simulation of failures will determine if the critical failure is detectable or isolated as declared in the FMECA or FTA, but at the operational systems level. The stage operational support simulation will determine the impact of the occurrence of any failures during any specified sustainment lifetime. Unique to this simulation is that it allows the assessing of any mixture of maintenance paradigms, such as run to failure, preventative, condition-based, and predictive, to analyze operational trades, benefits, and costs in over 100 graphs. The stage simulation is cognizant of several things. 1. The test coverage of each sensor, bit, and all diagnostic fault group constituency. 2. All failures that are and are not detectable at any time during the operational diagnostic interrogation. 3. Includes all failure rate, failure modes data, and computes failure propagation knowledge throughout the system. And 4. Considers the impact of how the system is maintained and how it will fail in the future. The MBSA must consider the operational effectiveness of very low-level physics of failure analyses for safety and risk mitigation objectives. This area of PHM can become extravagant or ineffective if not strictly worked within diagnostics engineering as a means to provide operational and maintainability effectiveness assessments during design development. The first step is to determine the best candidates for health monitoring or health management at the operational asset level. With this approach, investment in the development of advanced sensor technologies is based upon the diagnostic effectiveness and value of the proposed bit for any PHM application. Maximizing the utility of MBSA detail will combine to provide PHM candidates that can be objectively selected on the basis of safety, risk mitigation, and operational value, rather than solely on the size of the corresponding PHM budget. Since this capability determines the test coverage of any proposed or deployed sensors or bit and is fully cognizant of the propagations of any failure to the lowest root cause, it is able to generate turnkey outputs of the FTA that considers PHM in the MBSA. The prerequisite for the assessing of the expected operational value of PHM-informed MBSA is the use of diagnostic engineering as the currency to 1. Select prognostic candidates. 2. Discover the impact on risk mitigation in the FTA. 3. Balance PHM with any other mix of maintenance requirement strategies, RTF, RCM, CBM, PDM, and non-recurring costing data to achieve a myriad of sustainment lifecycle requirements. 4. Transition optimized MBSA to the operational environment. The ambitions of any high-end MBSA will ultimately be constrained by the diagnostic integrity of the operational asset and its effectiveness to transition the quality of the resulting design to the operational environment. To this end goal, this video has identified a number of the more unacquainted but integral pieces in assuring that the integration of MBSA into the MBSE environment is a seamless and effective process. Please feel invited to discover the broadness of the data interoperability and the depth of the software components briefly described in this high-end process by visiting the DSI International website.